Okay, so the next speaker is Melinda Tóth from Budapest. She's going to be speaking about the textile process relationship in Erlang.
Thank you. From the IFL University. I know that it's hard to pronounce it, but thank you for the introduction, and you have tried it. So my talk is about detecting process relationships in Erlang programs, and in my talk I will start with a motivation. Then I will introduce you the tool into the tool refactorer, which is a background for our work, because I extend this tool with the process relation analysis, and I also use the representation of that tool. And then I will show you, of course, the model that I have implemented. So the main motivation came from the goal of refactorer, that to help the Erlang developers in program maintenance tasks and to support code comprehension. So just help in debugging and maintenance and bug fixing and other type of everyday tasks in programming. And refactorer is already capable to detect relations among the sequential part of Erlang programs. And now we try to extend it with detecting dependencies among processes, among Erlang processes. And we also like to include hidden dependencies, such as using ETS tables or databases or some other hidden dependencies which are not as clear as when you send a message and you see there is a message passing between two processes. We use static analysis, so our analysis is always an approximation of the real dependencies, because Erlang is a dynamic language, so we can't calculate everything statically. So our analysis is a compile time analysis. I already mentioned refactorer, so what is it? It's a source code analyzer and transformer tool. The main goal of the tool is to support code comprehension. It has a lot of nice features to support that. It has query language, and the Erlang designers and programmers can ask semantic information dependencies among the different parts of the programs. It has, for example, a dynamic function call analysis, and it can generate a call graph with dynamic call information about the source code. So lots of useful things when you try to understand the source code, and you have to understand what the source code does. So besides this, it of course a refactoring tool. That's why the name refactorer. So it supports more than 20 program transformations. So it introduces more than 20 refactoring steps. It has features for measuring structural complexity metrics. It also implements clustering features for module and function level. And of course, we also have to plan clustering on processes after I have finished the process analysis. And it has several user interfaces. So Erlang developers mostly use Emacs, so we built it to Emacs, but it also has a VI interface. It built to Eclipse also, using Erlang. And I think the most popular interface in our industrial, for our industrial partner is the web interface of the tool, because multiple developers can use the same database and can use the same analyzed source code just through a web browser. So that's very popular. Just a few words about the design goals of the tool. We planned to analyze it, capable to analyze large code bases. Because the original idea of refactorer came from one of our industrial partners, the Hungarian Ericsson, and that's why they have millions of lines of Erlang code, so we must handle them. So that's why we choose a model that is persistent, because analyzing millions of lines of code takes time. So and And if we want to reanalyze the source code before every question, you can't use the tool. I can show you an example. Analyzing 2.5 million of lines of code with the Nisia backend of the tool takes 12 hours. So you do not want to wait it in every day or every hour, so you can't wait it. But our tool is incremental. So once you have analyzed the source code, and after you change something in your source code, we analyze only the change parts. So it's easy in that way, to do it in that way. So we store everything. We have 3 backends. We have Amnesia backend. Amnesia is the built-in database for Erlang. We have a C++ graph representation that's stored in the file system. And we also have a backend that using the Kyoto cabinet database. So we have 3 backends. The most tested is the Amnesia backend, but NIF version is, I call it NIF because you use Erlang, C++ functions from Erlang as a native implemented function, so that's why it is our NIF backend. So the C++ graph is the NIF backend, and it's much faster. So using C++ functions is, for storing the graph is much faster than using the Amnesia backend. To guarantee speed, we use asynchronous analysis. So every independent syntax part of the program is analyzed asynchronously as a separate Erlang process. And of course, we need an efficient data retrieval from the huge code base. So that's why we developed a graph representation to gather the information. And this is a 3-layer graph. It's labeled, routed, and directed. So when you need some information, you should not traverse the whole graph. You just give the sequence of labels, and you just jump through the labels, and you get back the information. Of course, it's a refactoring tool. We have to store all of the tokens, white spaces, comments, because we have to give back the original layout of the program after the transformations. So it's necessary. We have a syntax tree. It's defined by our own language description. So we generate a parser from our own language description. It's better because we can easily extend it, change some rows. For example, if 6 months later, once the hash groups will add it to the language, we can easily adopt our syntax representation to handle these kinds of changes. And we have a semantic level, and this is the most interesting part of the tool because it contains the semantic information about the source code. And there are so-called simple information such as function relations, variable binding structures. So just the simple ones, but there is also, for example, data flow information or dynamical information in the semantic level. And now we want to extend it with process information also. Here's an example graph. It's just for 3 Erlang lines. So you can imagine that it's a huge graph. And now back to the concurrent part of the Erlang. So that was the background. Just see that which are the language elements which we are working during the process analysis. So in Erlang you can create a new function, a new process with this spawn function. You can also register it. You can send messages to the process, and you can receive messages. So these are the basic language constructs for the Erlang actor model. And we analyze these constructs. And as I mentioned, we also analyze ETS tables. It stands for Erlang term storage. So you just put some Erlang term to an ETS table, and another process can read it from it. So it's some kind of shared memory in Erlang. we heard it from Natalia that Erlang processes doesn't share data, but they can. They can use ETS tables to share data. And there's a library to use ETS tables. And we think that these kinds of data sharing is something like message passing. So you just, it's like sending some data. So they are using the same data, so that's why we call it hidden dependency, hidden communication. And we try to analyze it. We represent the processes in a graph, of course. It's part of the refactoral semantic program graph. It's, of course, labeled and directed, and the nodes of the graph represent a process. A node in the graph represents a process in the system. Since Erlang processes are executing a given function, we identify the processes with the module that implements the function, the name of the module that implements the function, the name of the function, and its arity. So let's identify a function in Erlang. We identify the processes with that triple. And we introduce different edges, spawns for creating a process, register for registering a process. Of course, we have message sending, and this triple is related to ETS tables. So you can create an ETS table, read some data from it, and write some data. So we do not use send for ETS tables because it's a bit other type of communication. So that's why we introduce new IDs for it. And we have a special node called super process or something like that because you can just simply call a function from the Erlang VM, from the Erlang shell. And it's also a process, so we just have to note somehow that it exists. So this is the root of our graph. And those functions that doesn't belong any process belong to the super process because it can call from the Erlang VM. There are 3 steps. At first, we have to identify the processes in the source code. Then we add the communication edges through using the message passing information, and then we analyze ETS tables. That's now the hidden communication edges. And since Erlang is a dynamic language, when you call a function or create a new process, you can say that here's a variable that contains the name of the module, here's another variable that contains the name of the function, and here's a list containing some data. And you can spawn a process with that non-constant constructs, with Erlang terms. So we have to calculate the values of variables, the values of expressions, to know that which are the spawned process. That's why we use data flow analysis. And the refactorized graph already contains data flow information, and these are only the direct data flow edges, and we use a relation, it defined in a previous paper, called data flow reaching, to calculate the real values of expressions. Here's a bit simplified example from the paper. Just see some constructs from it. We register a server. The server waits for messages from the clients. The clients can connect to the server, and the clients can send jobs to be executed by the server. Once a server receives a message from the client and tries to execute the job, it reads some data from an ETS table, execute the function, and then insert some result to the ETS table. So this is the form of the hidden communication between two processes. Of course, the client process writes some data to the ETS table, the server process reads it, transform it maybe, and write another data, or some other data to the ETS table. And of course there is a client. the client connect to the server, create the ETS table with the ETS new function. So that's how we can create tables. Then spawns an input process, and this will read the job to be executed. And in each case, it will initialize the data in the ETS table. And if it gets a job, it just sends back and send the job to the server. So we want to create a process graph for that example. So at first, there was the process identification. The first step is to identify the spawn processes. Then we have to identify those functions which takes part in communication, and after the process that function belongs to. It can be a spawn function, of course, and it can be another a non-spawn function that belonging to the super process, so it can be called from the Erlang shell, for example. And of course, we should add the process registration information. So back to our example. Here's the spawn link for spawning a new process. So where we spawn the new a new server, I have to know that which are these parameters. This is a macro which stands for the name of the current module, so it's like a constant. Here's another constant init, and an empty list, which means that the arity is 0. It's a very simple case, but in some cases there are variables and expression here, so that's why we need data flow analysis to calculate the values of different expressions. Okay, so we identify the process, and the start function is starting this process. So there is a relation between the start function and the spawn init function. There is another spawn here. It's simply the start function from the client module. It's another start. It's from the client module, and it's spawned the input loop. So there are 4 processes in the graph. 2 is linked to the SOPR process, and there is the spawn and spawn link relations between them. As I mentioned, we also have to identify the process name registrations. Name is a macro for job server. I identify the spawn process with the job server identifier. So I just simply add this information to the graph, that the server start 0 process register, and then we can use also the job server to refer in this process. There are other communicating functions. For example, here's the connect function. Connect can, somebody can call this function, and it simply sends a message. So I have to identify the process, where does it belong to. I just traverse the backward call chain. I find that here's a function called to that connect function. It's from the start function, so it belongs to the client start process. And there are also lots of message passing expressions, so there are lots of information. But there is no new processes. All of the communication belongs to client start, server start, client input, and server input functions. So I have to add the communication. For that, I have to identify the message passing expressions, so the message sending expressions. Here's one. I send this tuple to the loop process. Of course, data flow analysis, I have to calculate the value. I have to know that what is the process identifier this loop refers to. So I have to traverse it back. This loop came from here. This is the parameter of the input function, but the input function is spawned, so I find the value here that is referring to the process identifier of the actual process. So I know that this loop is referring to this process. So I add the edge. to this link to the graph. And there are also other, of course, message passing. So I have to examine all of the message passing expression, find the corresponding receives, and add the receiving processes, and add this information to the graph. You can see that here are function calls, and the start, and the loop function calls that message passing expression, but the loop function is, belongs to the start process. So that's the message sending communication. Now the ETS tables. At first, we create a new process for each ETS table. That's because F tables is processes in the Erlang system. So they are new processes, and we also represent it as processes. So I just, when I find an ETS new call, I just simply add a new process to my graph. And there is a very important information in the option list that is a name table. It's something like I registered a process. After it, I can refer with the data atom to the ETS table. So I can use it as a reference to the ETS table. So I add it to the graph. Client start creates the ETS, the data ETS table, and I have to look for ETS table modifications. Here's one in the server process, but there is a variable here. What is the value of the variable? I have to go step by step back and using data flow analysis to calculate the value. I can illustrate it that how is it goes in this example. The tab is a parameter of the function. I call the function from here. That gets the results from the message. Of course, I need data flow analysis through message passings. So the messages came from here. There is also a binding here, so I just step back here. And this do function is called from the client module, so our data flow analysis have to be intermodular. So I step back to the client module. Here's the tab variable. That is a parameter of the function. And finally, here's a function call that contains the data at atom. Then I know that in the server, so in the server, the value of this variable can be data. So this server manipulates the same ETS table. And there are other ETS manipulations in the graph, and I add these edges also. So there are write operation stands for writing some data to the database, and reading for ETS select and ETS match when you get some data, read some data from the ETS table. I ran out of my time, so I do not want to summarize my presentation, just to say you what's next, because there was only a few language constructs that we have examined now, so we want to extend it with other Erlang OTP libraries, for example, RPC calls. So there is just hiding message sending and creating processes and the communication. So we want to analyze the OTP libraries, stands for the communication. And we also want to extend it for the distributed part of the Erlang, because now we are working just processes in a single node. So we want to extend it for the distributed part when a process can spawn to another node. So we will add nodes to our representation, and process will belong to nodes. And of course, as I mentioned in the first slides, for example, we want to add other type of hidden dependencies, such as dependencies through databases. For example, through Nigia tables, it's similar as when you use ETS tables or text tables or files. So we want to add these kinds of information too. It's just where is our homepage. I hope that the next release will contain these implementation. The current release contains the ETS table analysis and the message passing analysis so the data flow analysis through the message passing. So the release already contains it, but we are working on it, and I hope that the next version of the tool that we released in October will contain this analysis too. So thank you for your attention.
Questions?
I was just wondering how refactor to differ from
Wrangler.
Right.
Yeah, we have a completely different representation. So Wrangler uses an annotated syntax tree to represent the source code. And we use a semantic program graph, and when you want to gather some information from the Wrangler's representation, you have to traverse the whole syntax tree. For example, if you want to know that where a function is referred, where are the function applications, you traverse the whole tree. In our graph, you can just search the semantic function node, and there are direct links to the function calls. So the data retrieval is more efficient from this graph representation. And Wrangler doesn't store the analyzed information. So if I'm right, they only just analyze it in memory. And if you want to run another analysis, they will reanalyze the whole system.
The examples you showed were examples in which you build the graph to do refactoring on an Erlang program. What would be a typical useful refactoring for an Erlang program, since it's a distributed?
It's not really. So this graph is not really for refactoring. It's more for code comprehension.
Oh, okay.
So just for the Erlang developers I can visualize it in a graph, and they will know the relations among processes. When you want to debug something, that what's wrong, why I'm sending a wrong message or something like that.
And ETSs, you said that they can be used for sharing memory, but do they have a synchronization mechanism?
Yeah, it is in the VM level.
So is it like monitor or?
No, I don't know exactly how does it work, but it's implemented in the Erlang virtual machine. So I think they lock the ETS tables when multiple processes want to use it once. And you can also say that it's a private ETS table and nobody can use it, just me. So it's a kind of storage, but it's a possibility to share data with other processes.
Okay. Any more questions? No? So let's send the speaker.